Thank you. Yeah, so it's great to be here. Great to see so many old friends. So many of you I first met actually in Cambridge about 10 years ago. And at the time, Jason and I and Tetsuo Deguchi and various people were thinking mostly about random polygons, which for the purposes of what I'm talking about, I mean embedded piecewise linear closed curves in R3. And so we think of these as very simple models of polymers. And it turned out that there's a very beautiful geometric theory of these things that involved quaternions and Grassmannians and symplectic geometry and et cetera, et cetera. But that was kind of accidental in two different ways. So the first way it was accidental was that it was very special to 3 dimensions. A lot of the sort of beautiful geometric structures were kind of an accident of the fact that we were looking in 3 dimensions, which of course is relevant to the kind of physics we were interested in, but mathematically is kind of an accident. So that's one way in which it was an accident, and I think Jason, maybe tomorrow, will talk about some work that he's been doing with Henrik Schumacher on, okay, well, what about other dimensions? Like what's the mathematics of polygons in other dimensions, and sort of a theory that handles every dimension kind of all at once, and also does much better numerics than we were ever able to do. Okay, so that's one way in which the beautiful geometry that we saw was kind of an accident. Another way, so let me build up to the other way in just in a little bit. So the basic problem if you're trying to model polymers in this, I mean, this is a very naive polymer model. Of course, there's molecular dynamics simulations and all atom things and whatever. Like we're trying to do stuff that you can do on your laptop, not stuff that you need a supercomputer for. So at a very basic level, you say, okay, well, my polymer is made up of monomers, and if I understood the distribution of monomers in space, that would tell me what was going on with my physical system. Now, of course, your monomers are, they're interacting with each other. There's chemical bonds between, adjacent monomers along the polymer chain. There's some sort of steric effects, the chain can't pass through itself. There's, maybe, different types of bonds than weak bonds or whatever. So there's interactions between these things. And so we're going to model those interactions just saying, like, if there's an interaction between monomers, we're going to, think of there as being an edge, an abstract edge between those 2 points. And so really, you shouldn't think of your polymer as just a collection of sort of monomers floating in space, but, as built out of some sort of graph structure. And so in the random polygon story, the graph was a cycle graph, just a closed loop. And then, some of the really beautiful geometry came out of the fact that we were looking at cycle graphs. But if you look at more complicated graphs, some of the really special geometric structures kind of disappear. And so that was the other way in which, this theory we were developing 10 years ago, was kind of accidental. The accident of focusing on cycle graphs. Linear graphs also, have basically the same properties, but yeah. So what I want to talk about today is, okay, well, what can we do in this, still in 3 dimensions mostly, although actually the theory doesn't really care about the dimension, but with more general graphs. Okay, so here's sort of the conceptual setup is that we have these interactions between different monomers, which we're thinking of vertices as the graph, and the interaction is modeled by an edge in the graph. And then those interactions are symmetric probability distributions. So meaning like spherically symmetric. So it doesn't really matter what direction the edge is pointing in. What really matters is, something like the distance between the monomers. And so if you're just doing a linear polymer, everything is easy. You just say, okay, well, pick your favorite distribution, sample an edge from that distribution, take that edge, now do it again, and just concatenate these edges and just keep going until you have however many edges you want, right? So these are all, so this is just a picture of in this case, my distribution was uniform on the unit sphere, so they're unit length steps, but you could take, Gaussians or, any other distribution in R3 that you like. And if you're just talking about a chain, then you're like, great, that's easy. It's just, it's all the edges are independent of all the other ones. Statistically, it's very simple. Geometrically, it's a product space. Everything is easy. But if you have a more complicated graph, the edge vectors can't be independent if they form a loop, because you're saying like, well, as I go around the loop, that's like summing the edge vectors, and I'm requiring the sum to be equal to 0. Well, that's they can't be independent if they're required to sum to 0. So that's sort of the problem, is that this classical theory from the 30s of random walk models of polymers. Once you start having loops, you have constraints that destroy independence and make things much more difficult. Okay, so I'm going to use this phrase topological polymers, which I think was maybe coined by Teska, but maybe even earlier. So I'm just going to think of a topological polymer as something which is modeled on some graph or multigraph. So cycle graph, some sort of subdivided theta graph, some more complicated graph, things of this nature. Okay, so now, of course, the chemists thought about this a long time ago, and really going back to the 40s with James and Guth, and then Flory and Eichinger and various people. So the elasticity theory, if you think about it in the right way, is basically a theory of these topological polymers. And so the idea is you have some structure graph, and then in this phantom network theory or elasticity theory or James Guth theory or whatever you want to call it, you say, okay, great. I'm going to think of each of the edges in this graph as being, a Gaussian. And if the graph had no topology, if it was just a tree, they'd just be independent, identically distributed Gaussians. But then we're going to condition on the fact that we form all of these cycles. That's some linear subspace. And conditioning Gaussian distributions on linear conditions is a fairly straightforward thing to do. So I'm going to get some Gaussian conditioned on the graph, and then I can think about, for example, random embeddings of these things or statistical ensembles of these things. And one thing you might be interested in is like, well, what's the expected size of variations? So the expectation of the sum of the sort of the squared variations of these positions. And this, in some sense, goes back to these papers from the 40s, is expressed, also in this paper of Estrada Hatano. And what they say is, okay, well, this is in D dimensions. So usually D is going to be equal to 3, but it doesn't have to be. And then this fractor V is going to be the number of vertices in my graph. And then this L is this matrix called the graph Laplacian, which is a matrix you compute from for example from the adjacency matrix of the graph. So this is some matrix, and then the plus means that this is the pseudo inverse, but I'm taking the trace of the pseudo inverse, so this is just the sum of the eigenvalue, the non-zero eigenvalues, and the eigenvalues of the pseudo inverse, the non-zero ones are the reciprocals of the non-zero eigenvalues of L. So this is just sort of the sum of the reciprocals of the non-zero eigenvalues of the graph Laplacian. Okay, so this is kind of an amazing, this graph Laplacian is sort of a very nice sort of spectral graph theory object that people have, thought a lot about, very combinatorial object, and the fact that you get this beautiful answer is very cool. And like for this particular graph, the answer turns out to be this number that's about 4/3, but explicit rational number. Okay, so that's elasticity theory. Here's the problem from my perspective, is that this classical elasticity theory is very sort of fundamentally based on the idea that the edge distributions are, you know, zero-meaned Gaussians. And, you know, it's that assumption is really sort of built into the theory at a very deep level. And it, you know, sort of, in some sense, well, when you first look at this, you're like, it's sort of implicit in the appearance of this graph Laplacian. And it's very hard to untangle, like, where, you know, so this graph Laplacian is reflecting something about basically the topology of the graph. But it's also, its appearance in the setting is tied up in the fact that you're making this assumption about what kind of edge distributions you're looking at. You're looking at these harmonic springs, these Gaussian distributions. And it's, you know, when we started looking at this, we're like, wait, is this, you know, something that is more basic, or is this really only because of the Gaussians? And so trying to disentangle, like, what parts of this theory sort of work for arbitrary distributions and what parts are sort of very specific to the Gaussian setup is not so easy to do. So that's what I want to talk about, is like, okay, well, let's come up with a formalism which is sort of agnostic as to, you know, what edge distributions you're talking about. You know, you have some general theory, and then for any particular distributions you might care about, like Gaussians or like other things, you can plug them into the theory and see what comes out. I guess I should, you know, say, for my purposes, you know, the topology that's coming up is the topology of these underlying graphs. So it's not like knotting. Knotting is sort of a secondary effect. Like, you know, if you think about, okay, I have closed loops, and then I stick them into space, then, you know, how they sit in space, you know, is going to correspond to different knot types, and you know, all the different topology there. But I'm thinking of, you know, from my perspective, for the purposes of this talk, you know, the knotting case is boring because it's all circles, and, you know, it's always the same circle. So the topology is sort of prior to the embedding in this talk. And then, of course, like, once you have a theory that can account for arbitrary topologies, then you can start doing embeddings and saying, okay, well, what's, you know, what is the knottedness or linking or whatever of your embeddings of these different graphs? Okay, so fine. Now, this classical elasticity, you know, like natural elastic materials, think about rubber or think about, you know, elastomers or whatever, tend to be these very large, very complicated, you know, molecules, which, you know, you can at least think of as sort of random graphs. So big, complicated, randomish looking things. But in material science, you know, there's a bunch of synthetic chemists who are interested in, okay, can we synthesize relatively small topological polymers where we can control the topology? And then the idea is the topology will control the material properties. So, of course, you know, the properties of a material come from lots of different sources, but you say, okay, well, what about, does the topology, you know, give you something with the material properties as well? So this is a picture that I think Jason took of a beaker full of theta curves in Tezuka's lab in Tokyo. And so you can see, you know, those are theta curves. Those are topological polymers just sitting there in the lab. And so, you know, cyclic polymers, you know, I guess the theory of synthesizing these maybe was first sort of developed like in the 80s, and now people are starting to be able to produce these in sort of industrial quantities, but these more complicated topologies. So here's a sort of a picture of all of these topologies have been synthesized in the lab. You can see up here this K33, so a complete bipartite graph on 3 and 3 things, various other things like this. So these have all been synthesized and many others as well. So Tezuka refers to this as sort of a Cambrian explosion of synthetic topological polymers. Okay, so we want a theory that can kind of handle this sort of thing. All right. So here's this sort of ansatz. We are going to have these edge distributions. And again, I'm going to sort of require them to always be invariant under rotations. So spherically symmetric distributions. And if I just have linear polymers, then I'm like, great, I just, sample this distribution independently and concatenate them together, everything's fine. Not just linear, like if I have trees, like basically no cycles, everything's just going to be independent. But now if I have topological polymers, then somehow I need to condition on forming the actual graph that I want. And the question, of course, to ask is like, what the hell does this mean? It's not entirely clear what I mean by, sort of at a colloquial level, this kind of makes sense. But if you think a little bit more carefully about it, it's not so clear what it really means. So let's try to figure out what this means. So to set things up, I'm going to have to do some sort of basic algebraic topology. And really, this is sort of like the theory of like one complexes. So it's like simplicial homology or something, but just with one-dimensional things. So not super bad. All right, so here's the idea. So I have this vector space of vertex chains, which I'm going to call VC, which is just, okay, I have a fixed graph up front. So it has a fixed number of vertices, and I'm going to label the vertices 1 through scripty v. And then this vector space is just formal linear combinations of those vertices. And then likewise, okay, well, my graph also has edges. Again, I'm going to label the edges, and then I'm just going to consider the vector space of all formal linear combinations of edges. Okay, so far I just have these two vector spaces. Now, of course, they're related to each other because, every edge, these edges are going to be, directed. So that, these numbers can be positive or negative, so they correspond to an orientation along the edge. And so I have a directed edge, and then, each edge has a head and a tail, which are the boundaries of the edge. And so I have this map, which, is on each edge, it just is, gives it the head minus the tail. So this is a vertex. This is the vertex. This is the formal linear combination of vertices. So this is in that VC space. And the picture here's edge 4, and its head is V4, and its tail is V2. And so that's the boundary of V4. Now just extend linearly to the whole space. Okay. So there's this, I have two vector spaces. I have this linear map between them. And that now I have topology because, okay, well, what does it mean to be a cycle or a loop in the graph? Well, I think of my cycle as a sort of list of edges. So I think of that as a sum of edges. And saying that I'm a cycle says that, well, if I take the boundary of this sum of edges, it's 0 because the head is going to be the same as the tail, and they get subtracted. So the loop space is exactly the kernel of this boundary map. So here's in this sort of subdivided theta graph, you can see 3 cycles here. Visually, they're obviously loops, but if you think about, if I take the sum of all of these edges and take the boundary, it's for each of these is going to be 0. Okay. So now everything is a linear combination of closed loops, and we're going to this is a subspace that has a dimension. The dimension is what's usually called the cycle rank of the graph. Same thing as the first Betti number of the one complex. And you can easily compute that it's the number of edges minus the number of vertices plus 1. Or you can also compute it in this way. So the sum of the degrees minus 2, divide by 2, and then add 1. So in this, you can see that the degree 2 vertices don't contribute anything. So if I look at this subdivided theta graph, the only things that matter are these two, in terms of this computation, are these two junction vertices that are 3-valent. So I have 2 of those. So I get each of those contributes 1. So 1 plus 1 is 2, divided by 2 is 1, plus 1 is 2. And if you've never done this before, you say, wait, cycle rank is 2, but I see 3 loops here. What the heck? And of course, the answer is that if I take this loop minus this loop, here, this sequence of edges was oriented this way. When I subtract, it gets oriented the other way. Those things cancel. and I'm left with this thing here. So there's really only two basic cycles in this graph. All right. So that's just, the graph as abstract combinatorial / topological object. But what I'm interested in is, okay, well, now we have embeddings of these graphs into, again, usually R3, but in principle RD. Fine. So I need to somehow specify, well, where is each vertex in space? So, each vertex, so think of the list of vertices as a basis for this vector space. Each vertex gets assigned some position in RD, some vector in RD. And so the collection of positions is basically just the collection of all possible linear maps from this vector space into the space that I'm mapping into. And I'm calling it HOM because I'm going to do some stupid functorial thing in a second. So abstractly speaking, this is what the collection of linear maps from VC to RD. You can also think of this as just matrices, if that is less annoying. And so likewise, so vertex positions, the vertices go wherever they go, and edge displacements, and this is really like, what vector is this edge vector in space? Okay. And then there's this thing that I'm calling the displacement map, which says, okay, well, if I have a vertex position here, right, sorry, if I have a vertex position, I get out an edge displacement. And how does this work? So the edge displacement, remember, is a thing that inputs edges and outputs vectors in RD. So the displacement so X is a vertex position. It's going to eat an edge. And what it's going to spit out is exactly this. So it's going to give you the position of the head of the edge, the embedding of the edge, minus the position of the tail of the embedding of the edge. Well, that's exactly the displacement along the edge. That's exactly the edge vector as a vector in RD. All right. So now, so this is sort of natural. This displacement map is sort of the obvious thing, sort of physically, but it fits into some sort of commutative diagram. It's the same thing as the map induced by this boundary map after applying this contravariant functor HOM. So I go from vertex chains to vertex positions so vertex position is exactly HOM VCRD. Likewise, edge displacements was HOM ECRD. So that's this functor going up. And then, of course, it's a functor, so it takes morphisms to morphisms, and it's contravariant, so they go the other direction. And you can prove that this displacement defined on the previous page is exactly the thing that sort of comes from applying this functor to this linear map. Okay, and in particular, if my graph is connected, then the image of this map here is exactly the edge displacements which evaluate to 0 on any cycle. So they're exactly the things that correspond to actual embeddings of your graph. Like if this doesn't happen, if you have some cycle, but the net displacement as you go around the cycle is not 0, like you have not embedded your cycle into space correctly. Like it's not really a cycle physically, geometrically. So these are sort of the allowable, embeddings. Things that are not in the image of boundary star are not really physical things. They don't really make sense. All right. So now the space of all assignments of edge displacements which are compatible with the graph type is exactly this subspace. So that's what I just said. Like if you're not in the subspace, it doesn't make sense as an embedding of your graph. So these are exactly the assignments of edge displacement. These are exactly sort of the embeddings of the graph. So what we're interested in is, okay, well now we have to have some probability distribution on the actual embeddings of the graph, and this is where we need to live. So so in general, you have some some potentials on your edges. So you think of each edge as like Gaussian. right? That's really defining it on this ED space. You're just saying I have an edge, which is a vector. It has, you know, some distribution associated with it. But now conditioning on actually associating to the graph is like restricting to the subspace, which is harder. So it's easy to, you know, you want to understand your probability distributions in terms of this space, but you now need to sort of, you know, condition on this condition. So we're going to say a probability measure is admissible if it has finite first moment and it's invariant under the action of the orthogonal group. So it's sort of physical in the sense that it doesn't care. I mean, this is, I guess, isotropic, right? Like it doesn't really care about the orientation. And then, you know, informally, a probability distribution on the embeddings of the graph is just going to be a restriction of one of these admissible probability measures to the subspace that actually corresponds to physical embeddings, which has dimension d times the number of vertices minus 1. So it's, you know, again, if you think about like Gaussian edges or, you know, unit step edges, so each edge is sort of uniformly distributed on the sphere, but now you're conditioning on this condition, so now you're restricting to some subspace. And, you know, the subspace, you know, with respect to, let's say, Lebesgue measure is measure 0. And, you know, conditioning on measure 0 events is not necessarily such an obvious thing to do. So it's not always immediately obvious how to deal with the restriction of this is typically simple, but restricting is not necessarily so easy. All right, so let's first of all let's sort of recapitulate phantom network theory from this perspective. So now I'm thinking of Gaussians. So the distribution on edge displacements is just standard Gaussian, right? When I restrict to this subspace, it's just a restriction of a Gaussian to a linear subspace, still Gaussian. Very easy to deal with. So it's a standard Gaussian on this subspace. Okay, but if we're looking at sort of positions of vertices, so the actual monomer positions in space, that's some distribution over here on vertex positions. So what is that thing? Well, you have this distribution. You can push it forward by the pseudo inverse of this boundary star map, and you'll get some distribution on the image of this map, which is going to correspond to basically zero mean embeddings of your graph. So that's you map onto the image of this thing is the same as the orthogonal complement of the kernel of this thing, but you took your sort of nice standard Gaussian and you pushed it forward to some weirdo Gaussian, right? You take a Gaussian, you hit it with a linear map, it becomes some weird Gaussian. Which is kind of annoying. But it turns out that if you, so this, I'm thinking of just sort of the standard dot product on this space, which is just r to the d times the number of edges. Now on this space, so standard Gaussian with respect to that, you know, compute the covariance matrix with respect to this dot product. Now on this subspace, so in the previous picture, I had this sort of skewed Gaussian, which is the push forward of the Gaussian here by this linear map. But if I change my inner product, that weird Gaussian becomes a standard Gaussian. So the point is, like, you know, what was that weird Gaussian? Well, it was really just a standard Gaussian with respect to a different inner product. And what is that inner product? Well, it's defined in this way. I say, okay, well, the inner product of x and y is going to be the usual dot product of x, not with y, but with some linear transformation of y. And what's the linear transformation? Well, it's going to be L star, which is induced by the graph Laplacian. So this is really why the graph Laplacian shows up in phantom network theory. And the slide I showed you earlier is exactly because of this phenomenon. The tilde is to deal with the fact that this thing is, it has a kernel, and we don't like that. So the L tilde is to fix the kernel of this thing. So to make this an honest, you know, inner product and not a degenerate inner product. But it's basically, you know, the graph Laplacian is showing up here. And with respect to this inner product, these maps going back and forth are what are called partial isometries, meaning on the orthogonal complements of the kernels, it's an isometry. So now, like standard Gaussian hit it with an isometry, it's still a standard Gaussian. So this was very satisfying because like this is why the graph Laplacian shows up, because it's sort of controlling what's going on here. All right, so now once you have this in place, it's very easy to write down an algorithm to generate, billions of these things. Okay, you have to do some initial so you have a particular graph, and so that's going to induce a particular boundary map, and so you need to compute the pseudo-inverse of the induced of this displacement map, this boundary star. So that's sort of an upfront one-time cost for a fixed graph. Now you need to sample, your edge displacements from a standard Gaussian. That's easy. And then you just need to hit them with this linear map, and that gives you the vertex positions. And so, for example, for this path graph, here's a random embedding of the path graph into R3. So, like I said, this is a one-time cost, and then everything else is very simple: Gaussians and linear maps. Cycle graph, okay, here's a random cycle. More complicated graph. So the junction nodes are in orange, and you can see where they end up here. So those are the degree 3 vertices. All the other things are degree 2. All right. Now, I say this, I'm like, great, everything's easy. It's just linear algebra, right? But here's the problem, right? Like if you have a lot of vertices and a lot of edges, these matrices can be very large. And this graph Laplacian is going to be sort of vertices by vertices. So if you have 1,000 vertices, you have a 1,000 by 1,000 matrix. Okay, maybe that's not so big by modern standards, but nonetheless, eventually you get very sad if you're dealing with extremely large matrices and you're trying to compute pseudo-inverses and things like that. But here's the thing. In these physical systems, the graphs tend to be of a very particular type, where I have some fairly simple sort of template, and then I say, okay, well, but in reality, it's like I have these edges, but each edge is, many persistence links long, so I shouldn't really think of it as one edge. I should think of it as, 10 edges or 20 edges or 50 edges. Where what the number of edges is like how many persistence links are along this, this section of the polymer. So in these polymer models, typically your graphs are of this form where I have a relatively simple underlying graph where I've now subdivided the edges many times. And so you say, okay, well, in this setting, right, all these little internal vertices are just degree 2 vertices. And so in the graph Laplacian, it's going to be very sparse because you only get things showing up in the graph Laplacian when you have an actual edge between vertices. So, certainly on these vertices, like their rows and columns are going to be almost all zeros in the graph Laplacian. So you have this very large but very sparse matrix. Surely you can do better than just, dealing with the gigantic matrix. So what can you say in terms of, this? In principle, this is a big graph, but it's kind of a little graph. So how much can you reduce the big graph to the little graph? And the answer is quite a bit, although, again, you have to do a bunch of stuff which is sort of inspired by algebraic topology, although you don't really need to do algebraic topology in some sense. But so if I have a subdivided graph, if I just look at the junctions, so in these pictures, this vertex, this vertex, this vertex, and that vertex, their positions in a random embedding are like some random embedding of the underlying structure graph, right? So now, of course, it's potentially some weird distribution on the edges of the structure graph, but nonetheless, it's, they are some random embedding of the structure graph. So then we spent a very long time figuring out, okay, this seems clear. How the hell do you implement it? Like, what does that really mean? What do you mean, like a structure graph, a subdivided graph? How do you actually sort of encapsulate this into the theory? And here's what we came up with. We say, okay, well, so the VC prime and the EC prime, think of that as that's the structure graph. And then the VC and the EC are the actual, the subdivided graph. And the point is like, okay, well, if I have, G prime and G, then, and I have a map from VC prime to VC and EC prime to EC, so two maps, and they should be chain maps, meaning that whether I first pick where to put the edges and then compute boundaries to see vertices, or whether I first compute boundaries and then stick in the edges, it shouldn't matter which way I go around this diagram, I get the same thing. So this is just saying, like, you know, I mean, the way to think about this, like in this picture back here, is I say, okay, this vertex in this graph gets mapped to this vertex in this graph, and this vertex to this one, and this one to this one, right? Well, then clearly this edge should get sent to sort of the sum of these edges, because it's, this edge connects that vertex to that vertex, but this is that, and that is that, and so the edge between them has to correspond to some path between the two endpoints. And this is just capturing what I just said in symbols. So, okay, well, when you do this, so I had this map from this graph into that graph, these compatible maps, these chain maps. Well, then when I apply the functor, if I'm interested now in displacements and positions, I get maps going the other way. So the distribution on my subdivided graph, which is maybe fairly simple, pushes forward to some more potentially complicated distribution on a much simpler graph. So I trade, the simplicity of the distribution up here, it gets turned into a complicated thing here, but it went from a very big graph in matrix terms to a very small graph in matrix terms here. So you can sort of trade off complexity using these diagrams. And so here's sort of the big theorem, which says, okay, if I have these chain maps, they should be injective and the graph should have the same cycle rank. So really the G prime is like a template or a structure graph for G. If you don't have this cycle rank condition and the injectivity condition, it doesn't make any sense. And then I have an admissible measure on ED. Again, think like a Gaussian or something fairly simple. And then I push it forward by F1 star. So the sharp means push forward in the measure theoretic sense. So that's going down this way. So I have a distribution here, on edges that sort of induces a distribution on vertex positions, and then I can sort of map down here. But what I want to do is push down here and then go this way. And the question is really like, does it matter which way I go around? And the answer is not really. There's this extra thing where I need to project onto the image of this map here. But that's sort of a technical condition, which is not super important. So the point is, like, here's where I understand the distribution very well. And then I apply, if I can figure out what's going on here, then I can basically do my whole and all my computations on this simple graph rather than on the giant graph. That's the content of this theorem, the statement is definitely complicated. But let me give you some examples of what comes out of this. So for example, let's say I have what we call a multi-theta graph. So this I've just shown like a typical theta graph, but I have two. So this is the theta graph. I have two vertices and a bunch of edges connecting them. Strictly speaking, I guess this is a multi-graph because I have a bunch of parallel edges between the same two vertices. So I have M connections between the two junction nodes, and then I subdivide each of those into N different edges. So this is M equals 3 in the picture, and N equals 1, 2, 3, 4, 5, 6. All right. And then, for example, if you're interested in, well, what's the, now I embed this thing in R3 or RD, where I'm just assuming Gaussian potentials on each of these edges, how far apart are these two junction vertices in my embedding? And the answer is D times N over M. How does this work? Well, the distribution on edges is simple. It's just a standard Gaussian. The allowable edge displacements are this thing. So that's some subspace. So the distribution there is still simple. And now if I'm looking at, well, what is the distance between these things? That's like projecting onto a coordinate direction, which changes the variance from N to N over M. And then the D, so that's on each coordinate I get N over M. There's D of them, so total D times N over M. Okay, well, what does this mean? Well, notice the denominator is M. So this is, and M is the number of arms between these two things. So the more arms, the closer these two junction vertices are going to be. So here's a picture where I have like 20 arms, I think. And in these random embeddings, you see that the two junction vertices, which are in red, get very, very close together. This is sort of like topologically induced myceliation, where you've sort of driven these things into the interior. And so now you can imagine if this, you put some sort of some atom, some molecule that doesn't like water, you want to drive it into the interior. This is a way to do that. So this computation, in fact, was first done by Tetsuo and Erica. But then we were very happy to sort of recapitulate it in this framework where it became almost a triviality. All right, so that was Gaussian. Now something really hard. We say, okay, well, look, let's not put Gaussian potentials on the edges. Let's say the edges are unit vectors. Like we're requiring each of these sort of bonded monomers to be exactly 1 unit apart. So in random polygons land, these would be equilateral polygons, but now it's like equilateral random graph embeddings. And I guess now I'm working in R3. We'll call these freely jointed networks because it's sort of like the network, the graph version of freely jointed chains. So if I have some graph and how do you produce this picture and how do you compute with these things if I have this fixing the edge lengths to all be equal to 1, which is not such a nice thing because just think about so the edges are constrained to be uniform on the unit sphere. That's a singular distribution with respect to Lebesgue measure. Now I'm taking this singular distribution, so okay, I have a bunch of edges, so some product of spheres, so singular distribution on ED, and now I'm restricting it to some positive codimension subset. So it's singular distribution restricted to a measure 0 subset. Like this is not at all clear like how to deal with that problem. And this was the problem even with just equilateral polygons. Like how do you really get a handle on the distribution of equilateral polygons? Like you have this singular distribution and now you're restricting it to some linear subspace where the edges sum to 0. All right, so. But we're going to use that theorem. We said, okay, well, look, like these are all unit vectors, but if I have a subdivided graph like this, well, then the distribution between the orange vertices is, basically sum of, unit vectors, which is, in the large N limit going to be going to a Gaussian, but in general is going to be now a continuous distribution with respect to Lebesgue measure. So, instead of having this very singular distribution, when you take sums of edges, you get a continuous distribution, and that's going to be much nicer. So now so the point is I have this graph, but what's the structure graph? Well, it's this thing, and the chain maps just say, okay, this vertex goes to here, here to here, here to here, and here to here. And then we're interested, for example, in what's the distribution or the expectation of distance between junctions in this model. Now, in principle, so this thing has, I think, 28 vertices. So the space that you're restricting to is 27 dimensional times d, which is 3. So in principle, this is some integral in some 81 dimensional subspace. Not so good, right? But the point is, well, we on this thing, it's no longer 81 dimensional. It's now, well, really 9-dimensional, but we use the symmetry, the SO3 symmetry, to reduce it to a 6-dimensional integral. So we turn a, well, I guess 78-dimensional integral into a 6-dimensional integral using that general theorem that I told you before. And so this 6-dimensional integral now you can do on your laptop. And so what do we get? Well, this is a comparison of the numerical integration with a Markov chain experiment. And there are error bars on this Markov chain experiment, but they're very small. And you can see that there's basically a perfect match. Incidentally, this also sort of confirmed that this Markov chain was a good Markov chain in this setting because it gives you the right answers. All right. So this is something, I'm very proud of, that you could actually compute this freely jointed network expected, junction distance very exactly. All right. So now let me conclude by just briefly talking about, okay, well, we have these subdivided networks. And what happens if you let n go to infinity? And because somehow in the n goes to infinity limit, maybe things become easier. The answer is yes, they do become easier. But does that still sort of correspond to something reasonable, from a physics perspective? And so I guess I've switched from fully jointed networks back to Gaussian networks, but somehow in the large n limit, it shouldn't matter so much. Like somehow everything should eventually be going to Gaussian as n gets very large. All right. So to state the result, I need this thing called the normalized graph Laplacian. And here's the definition. So on the diagonal, it's 1 minus twice the number of loop edges at the vertex divided by the degree of the vertex. So the diagonal corresponds to individual vertices. Off diagonal, if I have two vertices that are connected by k edges, then I get a term like this, minus k over the square root of the product of the degrees. And if they're not connected, then there's nothing there. So this is the normalized graph Laplacian. And the theorem is that, okay, well, if I look, so I'm looking at expectation of radius of gyration. So this is the mean squared distance to the center of mass, normalized by the number of vertices, because otherwise this would be going to infinity. And what do you get? Well, you get something that's 1 over the square of the number of edges. The trace of the pseudo-inverse of this normalized Laplacian, so just the sum of the reciprocals of the non-zero eigenvalues of this thing, plus the number of loops of the graph of the structure graph divided by 3, minus this stupid constant 1/6. All right. Now, okay, so this is telling you, like, in the large n limit, you get something. So notice all of this only depends on the underlying structure graph. Like there's no n's left. This is just your structure graph, the number of edges, this matrix that you can compute from it, which is probably small because your structure graph isn't so complicated, the number of loops, and a constant term. So this is something that should be. Yes.
Question, that sixth, is that the sixth from the Weil expansion?
Oh God. Good question. Jason, do you know where the sixth came from?
Well, there's that sixth comes up in the Weil expansion for Laplacian also.
Oh, wow. No.
We never really analyzed this thing. We're just like, okay, it came up, but yeah, well, we should go back and figure that out. Yeah, cool. All right. Okay, so this gives you some numbers which are, again, simple to compute, at least on a laptop. Now, okay, so let's compare to experimental data. So this is in the Honda lab in Tokyo. This is a size exclusion chromatography apparatus. Basically, you have some tube in here, and then you take your polymer in solution, you run it through this tube that has a lot of tiny little beads, and then depending on how big these things are, it kind of separates. I forget. I think smaller things move slower, and bigger things move faster. I think, but maybe it's the other way around. Anyway, and if you run it through enough times, you can sort of separate different sizes. And okay, so this is going back almost 10 years now. This is the Tezca lab. They synthesized these different polymers. So all of these things have exactly the same molecular weight. It's the same number of atoms, right? Basically, you take this template, this tree graph, and then you glue these purple nodes together in different ways, and you get these different graphs. So, exactly the same molecular weight, exactly the same atoms in all of these things. But if you run it through this fractionation, the size exclusion chromatography, they have different sort of what's called elution volumes. So if you normalize so that the tree has, elution volume 1, then this K33 is down to like 0.62. And this thing, they said, when they saw how small this is, they're like, this is really compact, exceptionally thermostable. So you can imagine like that could be important if you're trying to do things like drug delivery or whatever. You want things that are exceptionally thermostable. Okay, now let's compute this quantity and normalize so that this is 1. So divide what you get for each of these things by what you get for this thing. And you get these numbers, which don't really mean anything. Notice they're all rational numbers. But now if we plot these things, so this axis is these numbers, and the vertical axis are these numbers. And we were very excited to see that these line up almost on a straight line, which in some sense is shocking because this elution volume isn't really radius of gyration. Radius of gyration is some measure of size. This is some different measure of size that people kind of believe that they're correlated, but they're not really the same thing. And of course, what we're doing here is like this is some, there's no physics. It's just pure math, and we're taking some large n limit. And of course, n isn't really infinity in any of these things anyway. It's not really Gaussian, and but okay, that's pretty convincing. Now we said, okay, well, let's compare to a numerical simulation where we're actually computing the same thing. We're not computing, we're not looking at elution volume. We're actually looking at radius of gyration in the simulation. So this is molecular dynamics on the Tsumame supercomputer, and then from this you can estimate what is the sort of the ratio of the radius of gyration of what you get to the tree. And the molecular dynamics gives you these numbers. The theory that I said before gives you those same rational numbers. And then when you plot them, again, you get this extremely linear relationship between these two things. Now, of course, the molecular dynamics is taking into account all of the physics, right? It's looking at all of the atoms, all of the physics, interactions with solution, everything is included here. Whereas our theory is some very simple, pure geometry. There's no physics. There's no real forces. Some large n limit. Nonetheless, you have this, very, very good correlation between these two things. So that says that okay, you can do a computation which is simple to do on your laptop, which will capture sort of a lot of the information you would have gotten from some big supercomputer calculation. So that's this matches shockingly well. I mean, I don't want to really overstate things, but somehow the fact that this worked as well as it did was kind of surprising, at least to me, with both experiment and with simulation. So thank you very much.